I hope you all got either on paper or on some device the notes. Pretty much all the words you're going to see are on there, so you don't need to write down any words, and everything else is just pictures, which aren't going to do you any good anyway. Okay, so we're going to go really fast. First thing, I'm going to start with a little recap of stuff you've already had, and I hope by this point in the semester you realize that all of these things tie together, that soil and climate and geology all tie together and make the system the way that we see it. So the particular things that are going to be important for my talk today have to do with the trade winds, the differences on the islands between windward and leeward sides, which is determined by the trade winds, a little bit about geology, mostly the kind of rocks that the islands are built of and the ages of the rocks the islands are built of, and then what happens to rain. And that's what Cindy just mentioned. It's all driven by that. And then we'll go very quickly through the freshwater macrobiota. Actually, I'm almost ignoring insects, which is a dumb thing to do. Okay, so this is stuff you've already had. That these are the things that determine at any particular point on the island how much rainfall there is in each month, how much rainfall there is annually. The Hawaii Rainfall Atlas is online now. You can get all of that information, really great resource. So depending on the elevation of the point and depending on where it is on the island, the rainfall will be different on average. And then we're going to talk about flow. That is, once the rain hits the ground or hits the leaves or whatever, it eventually, by gravity, percolates down to the surface, and where does it go from there? What are the kind of things that influence that? Overland flow, flowing channels, and groundwater, which I'll hardly talk about. It's very, very important, and there's too much for today. Okay, so this is a picture of trade winds. So note that down. Okay, and they hit the mountains and form clouds. Note that down. Okay, and what happens? The rain falls, and it falls to the ground and flows down to the lowest point, and then from there continues on downhill. When I took a hydrology course, the first thing they said is water flows downhill almost always. There are exceptions, but almost always. So these are impervious surfaces. These are roads, and so concrete and the regular kind of asphalt anyway that people use now, water doesn't percolate through, so it flows on the surface. And this is kind of a model for what happens in more natural systems. The rain collects at low points and then continues to flow. This is a more natural system. It's a cow pasture, so it's not completely natural. What determines how much water flows like this has to do with the type of soil, has to do with whether it's been raining previously and the soil is saturated, or whether it's the first rain after a long dry period when the soil can soak up a lot of water. And then obviously it goes to the lowest point. You can see along here, there's in the cow pasture, there's water right flowing through the grass, but it's flowing downhill, and you can see over here where these trees are that there's probably a little channel there. So this is probably a more permanent channel. This is obviously a temporary channel just because it's a rainy day and the soil is saturated. Okay, so what happens between this moving water, which has energy, and the rocks that make up the islands? Okay, well first I mentioned where the rain falls, the nature of the underlying rock, and you know by now there's different kinds of basalts, and the flowing water can operate on those different basalts very differently. And it also, of course, rain falls on other kinds of substratum, so soils and gravels and so on, so it's not just basalt. But as the water moves, it cuts channels, and this is going to be important when we get to the habitats of the creatures we're talking about. The channel cutting follows a pretty specific process. It's all governed by physics, geology, but as a permanent channel, a permanent riverbed is carrying water flows, it erodes, and it erodes in two different directions. It erodes headward, okay, that is towards the head of the stream, so towards Molokai essentially, and cuts into the island. And then in some cases, certain situations, it also cuts the valley wider because there's erosion on the valley walls as well as headward extension. Okay, so then we're going to talk about watershed types and then finally stream mouths because that's the important point for the stream organisms. Okay, so windward, typically more rain, sometimes heavy rains, and it says at all elevations, but obviously you know it's not equal at all elevations. Okay, so this is a cliff, and you can see that there are little streams there. They don't flow all the time, but they haven't really cut valleys. It's just simply little channels that contain the water when there's water flowing, and not when not. So this is the north coast of Molokai, and you can see that it's rainy topside, and there's lots of flow down this day. Okay, so although basalt is relatively hard, water will continually wear it away. Combination of simply the flow of the water, and also, especially during high flows, materials that the water is carrying, gravel, boulders, and so on, that pound away. And so it cuts little channels. So this is very hard rock, but you see it's cut a channel here. Okay. Over here, it's a little more overgrown, but you can still see there's a channel. What this tells you, among other things, so this is a point you should know if you go hiking, the fact that there's very little vegetation here means that flow probably comes up to these points fairly frequently. So aside from the discomfort, you probably wouldn't want to set your tent up here because that might be underwater in the middle of the night. Okay, this is just another kind of basalt. You can see again that the water flow has carved this little pretty little waterfall thing here, and is continuing down into a pool underneath. Okay, so most of the channel cutting occurs during high flow events. So you don't see it happening. You shouldn't see it happening because you don't want to be there when it's happening. Okay, but in low flow you can see the results of that. And so this is boiling pots above Hilo, and you can see these depressions are dug by the swirling water as it goes down through this prismatic basalt here. Okay, so this is what erosion does, and this is how it does it on solid basalt. Okay, so I talked about the headward cutting feature of streams, that is cutting towards the center of the island. So this is actually the same stream here, but this is Mauka, so the rainfall is mostly up here. It falls down, and the stream is cutting into the side of the mountain. Okay, so it's cutting deeper and deeper, so it makes the river valley longer and longer as it cuts towards the center of the island. Okay, so headward cutting, channel extension. Valley widening, I showed you. I'll show you another picture, but it's just the same thing happening on the sides of the valley. And then the plainese, which if you went on the geology field trip, you saw. Yep? Yep. Okay, that'll be on the final. Okay, so again, this is cutting headward, but also you can see that there's rainfall on the side of the valley, so this valley is getting wider. This is the side of a valley on Molokai, and again, you can see that the valley walls are getting pushed out. So that makes the shape of the valley wider and wider. So where it gets wide depends on where most of the rainfall is. So in amphitheater-headed valleys like Manoa, there's more rain Mauka than there is down towards the ocean. So the valley is wide at the top, in the Mauka end, but it kind of narrows down as it gets to more seaward direction. So this is a function of where the rain falls and how much falls. So plainese. So this, if you imagine that the original volcanic structure was a dome, the erosion cuts into it, but there are places where the surface of the dome, the original surface, or at least the contours of the original surface, are left behind. So you can kind of imagine, if you filled in all the spaces, that this would be a nice, round, smooth hump. So kind of like on the road. Okay, so these things are called plainies, and you can see they're used for agriculture, and they're also used for building houses. So this is from the field trip. You can see up here, you can build houses on these flat remnants of the original volcanic structure. So in a place like Oahu, where flat land is at a premium, especially in urban areas, people build on these kind of things. Okay, so this is a valley that is on the windward side of an island. It's fairly broad, and we're going to talk about that in a second, but very, very deep. Going into, this is Pelikuno and Molokai, going in fairly deep. Okay, leeward streams are a little bit different because there's often very little rainfall in the lower elevations, and so most of the erosion, most of the rainfall is in the upper elevations, and most of the erosion is simply by the water flowing in the channel, not by precipitation. So the valleys are deep and narrow and often V-shaped. So this is famous Waimea Canyon, and you can see that the vegetation shows that it's a relatively dry site down here, but the channel is obviously very big. Of course, this is an old island, so there's been a lot of time for erosion to take place. Okay, so this is the contrast. This is a leeward valley. This is Makamakole on Maui. And this is a windward, and you can see the more gentle U shape here and the sharper V shape here. Okay, so that's two things that might determine the shape of a valley, but there's other things going on. Last week or the week before, when I was supposed to be here lecturing, this is where I was instead. This is a windward valley, but it's very V-shaped, okay? But it's on a young volcano, relatively. This is on the Kohala volcano. It's relatively young, and if you go further in the Hilo direction from here, there are two really big valleys, Waipio and Waimanu, that are very, very broad, and lots and lots of agriculture in the flat floor. But these are a little bit more up towards the Hawi end. And it's a fairly young volcano, and these valleys are still in the process of developing. Of course, they're all in the process of developing. There's no stopping point until they go under the ocean. Okay, now the third thing I had on that list is the place where the river meets the ocean. And we'll see why this is important for the biology of the creatures we're going to talk about. And there are all different kinds of stream mouths. Okay, and this will have an impact on the kinds of freshwater creatures you find in the stream. So this is just a list of things, ways that water can enter. So this is going across the Boulder Beach. I think if you saw the video yet, this was taken the same place that video was shot. And this Boulder Beach is open here. Sometimes it's closed. This grass gets knocked down when there's a big storm. Sometimes rivers can enter across sand. So these are very temporary channels. They change every time the tide comes in and reshapes the beach. Or they can go in as waterfalls over a vertical drop. Here's a Boulder Beach. You can see it's a continuous line of boulders across here. There's a pond over here. The level of the pond is above sea level, but water is flowing underneath these boulders. It's just percolating through. But when there's bigger surf, the boulder berm breaks, and now you can see the waves are going into that little pond that was there before. So these stream mouths are very dynamic. They change from day to day depending on conditions. Okay, waterfalls going into the ocean can be really high flow or moderate flow like that. So why am I telling you all this? One more thing. This was a poster that was up on campus. I don't see the date on there, but a while ago. And it was all over campus about climate change and freshwater in Hawaii. And so I asked students to say what was wrong with the poster, and most of them said they didn't like the colors. But what's happening here is these are our big name people. And Tom Jambaluka is the guy that made the Rainfall Atlas. But there's nothing on here about native biota in the streams. Okay, it's all about water for us, because we know it's all about me. But if you look at water law in Hawaii, it's very specific. I don't expect you to have this memorized, but this is the part of the state law that set up the Water Commission and also says what fresh water is to be used for. So stream use means beneficial uses for these various purposes. And you can see that aquatic life and wildlife habitats is very, very high up on the list. So one of the reasons to conserve water or to keep water in streams by law is for the stream biota. So maybe they shouldn't have skipped it. Okay, so what do we see when we look in a Hawaiian stream? And from now on I'm going to be talking mostly about the biota, the creatures that we see in the stream. And you had or will have a talk, I think, on freshwater algae, so I'm going to limit myself to animals, and mostly bigger animals. So this is where I was when I was supposed to be here lecturing. So this is counting fish in the stream. That's me trying to stay in one place. So what do we see when we look there? What kinds of animals, as I said, I'm going to limit myself to animals that we see. Okay, so this is just sticking a camera in the water and snapping a picture of the bottom. So are there any animals in this picture? Well, there's lots of animals in this picture, which you can probably see better than me. There's prawns, there's, well, you can see them, I can't say fish. So these are the sorts of creatures that I'm going to be talking about for the rest of the time here. And I'm going to talk about, I'll show you pictures of them, but I'll also, and more importantly than being able to recognize them if you see them walking down the street, is their life history requirements and characteristics. Okay, so in this course you've had a lot of talks about birds and insects and all kinds of things, and one of the points that probably all the lecturers on those topics made is, okay, we've got these islands that are true oceanic islands that arose without ever having a connection or even a close location to mainland sources of animals and plants and microorganisms and so on. How did these things, where did they come from? What's their biogeographic province? How did they get here? What was the means that they got here? And once they got here, what did they do? So questions of speciation, adaptation, all the kind of stuff that you've been hearing lots and lots about. So this is the outline of the rest of the talk. I'm going to talk a little bit about ecological origins, biogeographic origins, and then I'm going to survey what we see and then talk about life history characteristics, and this is probably the key point, and then a little bit, if there's time, about threats to Hawaiian stream. Okay. So this is on your handout, so don't write it down. The dominant fishes, gastropods, and crustaceans, so insects are not there, and there's a reason for it, are marine in origin, and most of them retain the marine heritage in their life history pattern. So if you think about marine animals, so let's say coral reef fish. Okay, the adults live on a coral reef. They mate, they spawn, the eggs are laid or set free or however it happens, and the larvae go out to sea. And that's true of lobsters, that's true of crabs, that's true of most, or an awful lot, of marine gastropods. So it's the typical marine life history pattern. Okay, it turns out that the freshwater organisms in the category that I have up there have the same life history pattern. Okay, their original ancestors, or their ancestors, were marine creatures, and not necessarily their ancestors in Hawaii, but the ancestors of the whole group. And I'll talk about that in a second. And so they retain this life history characteristic. And as I say, insects and microfauna show different patterns. And that's mostly because their mode of dispersal is really different. Excuse me. Okay. Amphibians, I'll get to this word in a second, but this just says that. They show strong Indo-Pacific connections. Okay. So when you think about the marine organisms on the reef here, they show strong Indo-Pacific connections. So it's no surprise that organisms with marine ancestors show the same kind of pattern. So that's not what you see, for instance, when you look at Hawaiian flora. That's much more diverse where the plants came from. Okay, and it's also much more diverse in terms of insects and microorganisms. But because these things are aquatic and marine, they pretty much mirror what you see on coral reef fish, coral reef crustaceans, and so on. Okay, and I say this, others tend to be cosmopolitan, relates to this, although cosmopolitan is now a dirty word in biogeography, so make believe I didn't say that. Okay, so this is just pointing out that the islands are volcanic, that they arose far distant from any source of terrestrial organisms, and they started from scratch, bare basalt. Okay. What I'm going to do now is go through just showing pictures of the fishes, crustaceans, and mollusks of Hawaiian streams. And a little bit I'm going to go from the mouth to headwaters. So I'm going to do a altitudinal ocean to inland trip up a stream with my head in the water. So you can put your head in the water too. If you go outside, you probably will have your head in the water. Okay, so the most estuarine of the species is Eleotra sanbacensis. And again, all these names are on your handout, so don't try to write it down. All of the fish, all the native freshwater fish in Hawaiian streams are related at higher levels. Most of them are gobies. This is not a goby, and you'll see why in a second. But because it doesn't have one of the characteristic features of gobies, it's restricted to lower elevations. Any kind of sharp elevational change in the stream bed stops this fish from moving in. They're ferocious predators. They'll eat anything. It's a good thing if you have an aquarium with lots of guppies and expensive freshwater tropical fish to put one of these in, and then pretty soon you won't have any. Maybe that's not a good thing. Okay, you can see they have this terminal or sort of subterminal, very, very big mouth. This guy's sad because look how hungry he is. He hasn't eaten for a while. And what I'm going to do when I show you each of these is I'll show you a slide with the Latin name and a slide with the Hawaiian name. And as I said, these are all on your handout, so don't bother writing it down. Okay, this is a dead goby. And true gobies have their ventral fins fused together into a little suction disc. This is true of marine gobies as well as freshwater gobies. So it's a characteristic of the entire group. There are many, 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 many species of gobies. Gobies is a very speciose group in fresh and salt water. So in the intertidal, if you go hiking along rocky intertidal and you see waves breaking and little fish managing to hold on, this is how they're holding on. Okay, it attaches to the rocks and enables them to withstand water flow up to a certain point. Okay, you can see why such a thing might be handy in freshwater too. As I said, that first fish I showed you, Akupa, doesn't have that, and so it's not able to hold on to rocks, so it tends to live in estuary conditions. But the rest of the fish I'll be talking about, freshwater fish. So I'm leaving out things like mullet, aholehole, papio, barracuda, things like that swim into freshwater but are mostly marine. So everybody will be a goby. Okay, the next up is Stenogobius. This is actually very common in Oahu streams. It's not that common on other islands. But you can see, maybe you can see, the little suction disc that it has down here is kind of filmy. It's not very strong. So this fish also doesn't get very far upstream. It likes sandy bottoms. It buries itself in the sand. If you go to the stream mouth at Kahana or Ka'ala, these fish under the bridges, the highway bridges across the stream, they're very, very common in there. They're kind of pretty. Unfortunately, when you put them in an aquarium, they bury themselves in the sand, so you can't really get a look at them. But this is a picture now of the little disc, and you can see it's not very sturdy. Okay. Okay, moving upstream, and this upstream downstream thing is a generalization. They overlap to a great extent. Okay, is Awaustominius. This fish can get quite big, even now that there are records of them getting up to 30 inches long. The longest one I've ever seen is maybe 20 inches or so, but they get to be very good size. And this is the fish, if you go to Kauai in the end of summer, the very first big rain, if you're going across the bridge at Hanalei River, you'll see a bunch of guys out there fishing with long bamboo poles and earthworms. This is what they're fishing for. Some of these fish, especially the really big ones, in the first big rains of the year, so usually September, sometimes October, will swim downstream or get carried downstream, nobody knows which, and will spawn, and they'll have these huge spawning aggregations. And the females, a big female like this can lay a couple million eggs. And so you see these big patches of eggs on the rocks, and you see a lot of hole coming in and trying to eat them, and you see the poor fish trying to chase them away. So this fish is kind of whitish, and so that's how it got that name. Okay, moving further upstream, or actually moving into faster water, is Siceopterus. This is probably a juvenile. This is a male. There's another picture that shows this a little bit better. These fish are, there's another male down there. These fish eat mostly diatoms that are attached to the rocks. So it looks like this is pretty barren for fish food, but this green kind of scum here green scum is. Anyway, this green scum is composed of diatoms. And these fish have the mouth, I think you'll see it better in another picture, but the mouth is down below, so it has a snout that comes straight down. And then, so everybody here knows how great white sharks work. So you've seen the pictures, they open their mouth and then all of a sudden their jaws come out and their teeth are like on a separate little thing. People are looking at me like I made this up.
Sure.
Yeah, sure. Okay, these fish are just like that. Except that their jaws aren't full of big, sharp teeth. They're full of really interesting teeth that look like little combs, the top jaw. So the top jaw comes out of their mouth and hits the surface of the rock, and then they go and scrape off the diatoms. So as adults, they're very specialized feeders. This is a very blurry picture. It's a low-res picture, but you can see the males, especially when they're displaying, have this white stripe, and in water that's fairly murky, this is quite reflective, so it really stands out. So the males are making themselves very, very visible. I'll talk about sex in a little bit. Okay, this is another one. You can see they have a long fin here. A little bit of color along the bottom, but you can see the front of the nose is like straight up and down, like they swam into a mirror or something. Okay, so that's what the front of the face looks like. And these are can be very strongly attached to rocks. They live in the fastest water. So the name no pili pili means to attach, stick on, to be attached to. So these were often used in situations where somebody wanted like good luck to attach to a new house that they built, something like that. So these were used in those that are sacrificed for those kind of things, because like these things can hold on to the rock. You want the good luck to hold on to your enterprise, whatever it is that you're doing. Okay, this is a juvenile. This one doesn't show it, but they have this kind of checkerboard coloring, and their mouth hasn't quite become totally terminal. Another really interesting thing about these fish is when they recruit to a stream, which I haven't told you about yet, but you know it's coming, they look like regular little planktonic larval fish. And what happens, and this is like a real transformer kind of thing, what happens is in about 48 hours, actually less than 48 hours, the bones of the head completely rework themselves into this new shape. So this whole fish is transforming its skeletal structure in its head to be able to do this other kind of feeding. So there's been quite a bit of study on that operation. Okay, the last species of fish, and the one that tends to occur at highest elevations, is Lentipes concolor. These are females. There's an arrow pointing to these little rice grains because I don't have another picture of rice grains, but remember those rice grains. We'll come back to that. So these are females. That's a female. The only reason I put the slide here, which isn't very good, is this is the Hawaiian name, Alamo'o. And the reason why is they don't have very much in the way of scales. And they're kind of wriggly and so on. So one of the Hawaiian names, Alamo'o, is because they look like little mo'o, like little freshwater lizard things. And mo'o are usually bad news. If you run into a mo'o, you shouldn't be where you are. And so they were considered bad luck. And so they weren't generally eaten, and if you caught one, you kind of tried to get rid of it as soon as you could. So that's what was his name there. This is a male. The other name, Hiukole, is because the back end can be very, very bright red. So the males, when they're displaying, get really incredible. They get this fluorescent blue around the tail. These fins are brilliant white, the same as the stripe on the Opili that I showed you in the front end is dark, dark black. So again, in turbid water, these really stand out. So the males, when they're displaying, are very, very visible. And they get out there in the streams and they dance around and flash their colors and hope to attract females. Okay, then we have a couple of endemic freshwater crustaceans. So this Atuaea bisulcata is a little shrimp, and a Hawaiian name Kalaole. I'll tell you why it's called Kalaole in a minute. But they occur in some streams in really large numbers. And people like to eat them. People like to eat them. You see people collecting them and you toast them up. So if you go to a real party, a lot of times you'll get served these little guys. And they're very crunchy and tasty. I had a picture of someone eating one, but I took it out. Okay, we also have some endemic gastropods. We have, the ones I'm going to talk about today are neurids. So if you go to the shoreline and you see the little, you probably saw this if you did an intertidal field trip, little black snails that are white inside. They're called pipipi, and you can eat them. They're kind of hard work to eat, but you can eat them. Okay, these are in the same group as those. They're neurids. There's a couple of species. Neratina granosa is the bigger one, and you can see it has this kind of peach color. Neratina vespertina, this is much more, the shell is a lot more organic. This has a moderate amount of calcification. So again, these are eaten. Sometimes you see them in Komashiro Market. I think in your handout they're called hihibai. This one's called hihibai. Sometimes on the Big Island they tend to call them hi. Same. And this one, which tends to occur lower down, is called hapabai because it's a place where freshwater and saltwater mix together. So these are both endemic gastropods. Oh, there it is, hihibai or hi. And they go over the surface and scrape rock surfaces just like most other kind of snails. Okay, so now you can relax from pictures for a minute. This is again on your handout, so you don't have to write it down. But all of these creatures that I've showed you share the same life history pattern. And the term for it is amphidromous, and the definition is given there. Adults live in the fresh water. There are some differences in elevation, but it's not strict. The adults spend the entire life in a stream. They don't leave and go, I don't like this stream, I'm going to go find a better stream. they may get washed out in a big flood, and if nobody notices, they might survive for a couple of days in seawater, but nobody really knows about that. So essentially, once a fish is in a stream, a snail is in a stream, a shrimp is in a stream, they're there for life, unless you catch it. So egg laying occurs in a freshwater habitat. This downstream breeding migration is a popular notion, and it does occur, but this probably is more common. The eggs are laid in the adult habitat. Tiny fry hatch out, drift downstream. There's a planktonic period in the ocean, which is pretty long. Then the post-larvae find a stream, return to freshwater. How they do it, nobody really knows. And then they move up to the adult habitat. So, except for the fact that this is going on in a stream, and there's upstream and downstream movement, this is the same life history that you'd see in a coral reef goby and a coral reef butterfly fish or anything else. So the life history pattern, or lobster or crab or marine snail. So the life history pattern is just as the life history pattern was for the marine ancestor, except with this added problem of dealing with being in a stream. Okay, so this is an egg mass up here. This one, well, you can see how big it is. The males court females and entice them into a little cave or some other place. You know, come in, come in. Then the females will spread their eggs on the surface of the rock, and they attach. You can see how they attach here with these little fibers. The males fertilize the eggs, and then, and this is the good news, the males kick the females out and take over raising the, protecting the eggs. So it's a great thing for the females. Okay, so the eggs are attached to the rocks, and you can see them developing. This is the yolk sac, and you can see there's 2 cells here, maybe 4 cells here, and so on. So the development takes place inside these egg sacs attached to the rock, and the males are in there guarding. Okay, and what hatches out are very, very undeveloped free embryos. That's the official term for this early stage. What happened was nobody knew what larvae or what recruits belong to which species. Okay, because, you know, you look at that, I used to have these on separate slides, and people were going, why is he showing the same picture over and over again? They all look pretty much alike when they hatch. So Dan Lindstrom, who is at University of Guam now, got adults, got DNA from the adults, and then got DNA from the recruits and also from the larvae, and was able to assign the unknown stages to the proper species. So that's why now we can put these species on these different ones. The important thing to notice on these is they have no mouth, they have a huge yolk sac, they don't have a mouth, they don't have an anus. It's a good thing. If you have a mouth and not an anus, that's a bad thing. If you're not going to have an anus, it's good not to have a mouth too. Their eyes are very undeveloped, and they can barely swim. Okay, so these things are pretty much at the mercy of the stream flow. They carry downstream. It turns out they have to get to fresh water within about 7 days, or they blow up. Okay, so they're not able to osmoregulate. They have very little in the way of organs, so they can't do that. So they basically are crossing their legs really, really tightly and hoping to get to saltwater as soon as they can. You can see that they start to develop. Dan Lindstrom worked a lot on this. This guy now has a bigger eye, a mouth, and an anus, luckily both developed. But it's still a very undeveloped looking larva. And you can see this is the longest he was ever able to keep one. They're not eating. We couldn't find, well, he couldn't find the food that they eat. Normally by 14 days, they would be out in the ocean. Okay, they go out to the ocean and mix with all of the other marine plankton that you've heard about. Nobody knows where they go. For some of the species, we know how long they stay because, like all fish, or like most fish, they have an otolith, so you can count how many days they've been out there and how they return and when they come back to fresh water from the ocean. And it turns out they're out there for quite a long time. Typical reef gobies will be out for 28 days, 32 days, something like that. This one, which is the only one we have good data on, is pretty much a 90-day larval period. So that's about 3 times the normal coral reef goby marine life history. We don't know why that is, and we don't know where they go. We don't know a lot of things. Okay, they return, this is a terrible picture, this one is almost in focus. They return as Hinana, the post-larvae, the Hawaiian name is Hinana. They return to the stream, they're about 2.5 centimeters long, more or less, sometimes less. And they become benthic. Of course, when they're out in the plankton, you think they're pelagic. They become benthic, and then they start moving upstream to the adult habitat. They can move pretty quickly. The stream that I showed you where we were last week, we were finding relatively new recruits, 2 kilometers up from the ocean. So they move really fast when they're in the stream. And because a lot of these fish occur at high elevations, they occur above waterfalls. So there are gobies up here. And so the question is, how do they do this? This is a Falls. How do they get up these waterfalls? And that's always been a big question. So one of the solutions is this, which probably doesn't happen a whole lot. But what does happen, we believe, is one, they don't go straight up into the rushing water. Most big waterfalls have a lot of moss, ferns, wet vegetation along the sides, and we believe that they mostly make their way up there. Now, on small waterfalls, like maybe a meter or so high, where you can actually get close to them, like you can't do with the Kauhako Falls, you do see, especially Nopili, actually using their suction disc in their mouth and climbing up those little waterfalls. So they do go straight up rock faces. Those big, big waterfalls, we don't know. Okay, I'm going to end talking about threats to Hawaiian streams and their biota. So dewaterment, channelization, and alien species. This is a stream. This is a dam. Okay, so obviously nothing can get above that dam, at least when it's dry like this. So, and the water is being taken out of this pond behind the dam for a power station. Okay, this is a typical Oahu stream. This is Kava stream. This is channelization. This is not good habitat for native stream creatures. Okay, this is on Maui. This is Iao stream. It's great for skateboarding, but this little trickle of water here is Iao stream. So one, if you've been to the park up there, there's plenty of water flowing in Iao stream, but it's taken out of the stream for irrigation and other things, and the Army Corps of Engineers built this huge thing for floods. Now, it's got lots of graffiti on it, so I can't show those pictures because they're mostly X-rated graffiti, but this is what a lot of Hawaiian streams look like. Okay, avian species. This is Macrobrachium lar. This was brought here in the 1950s as an aquaculture wonder. It has an amphidromous life history pattern, so it can, it lays eggs. The females carry the eggs under the abdomen, the embryos under the abdomen, like a lot of crustaceans. Within 15 years of this species being brought here, it was released in Pelikuno Stream on Molokai and Kahana Stream on Oahu. Within 15 years, it was in every stream in the state. So those larvae really get around. We don't know exactly how it interacts with native species, but it's, they get really big and they can be very disruptive. They walk around like giant robots. Okay, a lot of people will bring me a jar of water from some cruddy stream. They say, look, 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 we've got opie in our stream. This is so great. Okay, what they've got is Neocaridina. This is, you buy this in pet stores. I think it's 10 cents each or something like that. People buy them and the fish don't like them and they throw them in the stream. So pretty much most streams on Oahu have this now. It's not amphibious, so it won't be in a stream unless someone put it there. Turns out they look a lot like, they're in the same family as the native shrimp. It's hard to tell them apart. So remember the name, one of the names of the native shrimp is kalaole. It doesn't have spines, okay? Like Libu kala is the sargassum is kind of spiny. So the Hawaiian species on this rostrum here, this little thing that sticks out in front, doesn't have any spines. If you look at the rostrum here with a microscope and magnifying glass, it's kind of spiny. So if somebody brings you a shrimp and says, look, 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 we've got native shrimp in our stream, and our swimming pool, and our cesspool, and stuff, okay, just take a look at the rostrum up here, and I'm betting that you're going to find it's this. Okay, so there's a lot of things we need to do to take care of our freshwaters, and paying attention to how we treat the water in the streams, and so please make this little guy smile. Okay, thank you.